Hi everyone, I am Erfan Maleki and I would like to present our study on the effects of hybrid post-treatments on fatigue behavior of notched LPBF aluminum-silicon-10 magnesium with two different experimental and deep learning approaches. This work is performed in the Department of Mechanical Engineering in Politecnico di Milano, which is a member of Ivy League in European universities. I'm a third year PhD student and this work is part of my PhD studies under supervision of Professor Mariano and Professor Sara Baghari. Also, this work is sponsored by Norblast Group in service. Here is the list of contents that I want to present. Firstly, I would like to talk about state of the art in the field of surface post-treatments for metal additive manufacturing. Secondly, I would explain the experimental procedure that we already performed. And then I would like to talk about implementation of deep learning, and then results, and finally conclusion. Here as an example, you can see surface morphology of fabricated AM materials using different technologies of selective laser melting and electron beam melting, considering different process parameters. Irregular surfaces with poor surface quality with lots of melted and partially melted powders and spatters can be seen on both fabricated samples by different technologies. As you know, mechanical failure, especially fatigue failure, is very sensitive to the surface of the mechanical components. If these materials have poor surface quality, we have low fatigue performance. Accordingly, in the field of additive manufacturing, as they have lots of irregularities in their surfaces, a great effort has been lately dedicated to developing post-treatments for improving the surface quality of metallic materials. Based on our previous study, it was obtained that the applied surface post-treatments on metallic AM materials can be categorized on 4 different groups of material removal, no material removal, coatings, and hybrid treatments. Shot peening is a mechanical surface treatment and cold working process which is used small impacting media bombarding the target, as you can see schematically here. By applying shot peening, compressive residual stresses in high range are induced in the surface of the material. In addition, surface of the as-built state can be modified in a good way. Also, by applying shot peening, considerable grain refinement in the surface layer can be obtained. These 3 factors and effects of shot peening resulted in fatigue behavior improvement of the material, as you can see in these studies. Different chemical treatments can be used as a surface post-treatments in the field of additive manufacturing. These chemical treatments are including chemical etching, chemical machining, chemical polishing, and electrochemical polishing. Here you can see effects of different treatments on surface roughness reduction and modification of surface morphology. In some cases, 2 or more post-treatments have been combined to achieve the desirable surface or bulk properties for the AM metallic material, based on the requirements of the final applications. Combining heat treatment HT and hot isostatic pressing HIP with various other surface treatments can be considered as the common combination of post-treatments applied to AM metallic materials. Here you can see the combination of heat treatment and sandblasting, and heat treatment and shot peening. In other study, application of etching, chemical etching on as-built state can be seen, which combined by PEO. And in another study, application of machining and polishing together on the as-built state is shown. You can see in all of these hybrid treatments, surface morphology modification is obtained, as well as biocompatibility improvements and mechanical and fatigue behavior improvements. In this study, effects of shot peening on the V-notched LPBF aluminum silicon 10 is investigated in terms of modification of microstructure and surface morphology, as well as the mechanical properties including hardness, residual stress, and fatigue behavior. Also, effects of SP-based hybrid treatments is surveyed. In the hybrid treatments, combination of shot peening with other treatments including heat treatment and electrochemical polishing (ECP) is considered. Afterward, a deep learning based approach was employed for modeling the fatigue behavior using artificial neural network. In development of neural networks, surface roughness, surface modification factor, hardness, residual stress, and porosities of the material were considered as inputs, and fatigue life was considered as output of the networks. Aluminium silicon 10 magnesium with powder mean diameter of 46.65 micrometer were used in this study, and also selective laser melting (SLM) as a LPBF technology were used. And here you can see the used parameters, and this is the shape and size of the fabricated notched fatigue specimens. In fabrication of the specimens, the values of 1 millimeter were considered to ensure that we can reach to the notch root by applying shot peening to this area, also in the both upward and downward skins. As post-treatments, half of the samples were heat treated using T6 thermal treatment, which is very common in aluminum alloys, and then shot peening and electrochemical polishing were used as surface post-treatments. In the shot peening treatment, steel shots with diameter of 0.43 millimeter with Allen intensity of 10A and surface coverage 100 was used. Also, in electrochemical polishing, pass of 400 milliliter solution of 94% acetic acid with 6% perchloric acid at voltage of 15 volts and duration time of 240 seconds were carried out. Here you can see the schematic illustration of applying heat treatment, shot peening, and electrochemical polishing on the LPBF samples, and also the obtained different 8 sets of specimens by applying different post-treatments. Now I would like to talk about deep learning and its application. The main goal of artificial intelligence-based systems such as deep learning is to create technology that allows computers and machines to function in an intelligent manner. AI-based system has some major applications such as prediction, modeling, optimization, knowledge representation, planning, learning, parametric analysis, and sensitivity analysis. In this study, artificial neural network (ANN) is used to model the phenomena by using a deep learning approach. ANNs, which is inspired from human's brain, are widely used as a powerful tool for prediction, optimization, and modeling of complex phenomena. Here you can see a schematic illustration of natural neuron compared to the artificial neuron. In the natural neuron, The signal and messages are received by dendrites, then they transfer to the cell body, and in the nucleus the data and the signals are processed, and then they transferred to other cells using axon and axon terminals. In an artificial neural network, the data as inputs are fed to the network, and then values of weight and biases are added to the inputs, and by applying some processing using transfer functions, the values of outputs are obtained. Here you can see a schematic illustration of a single neuron consists of summation unit and transfer function. Different functions of linear, tangential, and logarithmic can be used as a transfer function. Based on the depth of neural network, which can be specified by the number of layers, neural networks are divided to shallow neural networks, which maximum has 2 hidden layers, and deep neural networks. In the shallow neural networks, SNN, as you can see here, we have input layer, output layer, and 2 hidden layers. The inputs are fed to the network, and then we can obtain the outputs. In the current model of deep DNN, which is stand for deep neural network, we can see input layer, output layer, and 4 different hidden layers. In order to improve the accuracy of the obtained results, as we have a small set of data, we considered auto-stack encoder in between all of the hidden layers to pre-train the data and increase the accuracy of the results. In this study, as I mentioned before, yield and strength of the material, elongation, relative density, surface roughness, surface hardness, surface residual stress, and surface modification factor are considered as inputs, and fatigue life is considered as outputs. Also, the performance evaluation of the networks is performed considering the coefficient of correlation R2 with this formula. Details of the development of SNN and DNN are explained in our study, which you can see using this reference. After explanation of the experimental procedure and also implementation of the deep learning, here I want to present the results and discussions. The results and discussion sections is divided to 2 different parts of experimental results and modeling results, which are obtained by the neural networks. Firstly, I would like to mention to the monoclinic mechanical properties. It can be obtained that by applying heat treatment, the elongation is increased from 2.5 to 13, which shows high increasing inductivity of the material after heat treatment. Also, the values of yield and ultimate strengths were slightly reduced after applying heat treatment. Microstructure observation using optical microscopy, SEM and EBSD, were performed in both longitudinal and transversal section of the both as-built and heat-treated material. In the as-built state, you can see the traces of laser and the hatchings visibly, and after heat treatment, it can be observed that most of the traces are becoming visible, and the microstructures become more homogenized. In addition, in the as-built state, granular and acicular silicon in the shape of network fabrics network can be seen around the aluminum matrix, but after applying heat treatment, the silicon face is become to a spherical shape. In addition, porosity measurements were carried out using image analysis. Different cross sections in both as-built and heat-treated samples were used for backscattered SEM, and then the obtained image were binarized using imagery software, and then the fraction of black to white areas were considered as porosity of the samples. In the EBSC analysis, shot pin samples in both as-built and heat-treated condition were investigated. You can see, by considering the grain boundaries, high plastic deformation and high density of the grains in the top surface. Also, it can be observed that in the IPBF, which shows the orientation of the samples, different orientation of the grains can be observed in the surface layer, which placed randomly. In addition, G and D, which is the factor of dislocation density, shows the highest value in the surface layer, like here and here, which confers the highest rate of plastic deformation in the surface layer. Surface morphology of the samples were investigated using SEM. This is as-built sample. You can see high surface irregularities in different sections of notch area. In the downward face, the highest irregularities can be seen. This area has the poorest surface quality. Then notch root, and which is followed by the upward face, which has the lowest irregularities in the surface. Unmelted and partially melted powders can be seen easily, as well as the spatters on the notch root. In this study, for the first time, a parameter as a surface modification factor is described. Here we can see the comparison of the surface morphology in the as-built or heat-treated state, in the shot paint, and also in the electrochemical polished. You can see the surface quality is increased from as-built to shot paint and shot paint to electrochemically polished. Then to apply and develop neural network modeling, a novel criterion is assigned to each state. Numerically, we considered 0 for as-built, 0.5 to shot paint, and 1 for electrochemically polished. These values also considered for the as-built or heat-treated specimens, as well as the shot paint ones. Here you can see the obtained results of different experimental characterization listed in the table. You can see the increasing of surface hardness and visual stresses in the shot paint samples, and also it was observed that ECP had not any considerable effect on the hardness and visual stresses, and also density. Here is the results of neural network modeling. In figure A, two different SNN were compared. The first one has the one hidden layer, and the second one has two hidden layers. Uh, it can be observed that by increasing the number of neurons in each hidden layer, the value of accuracy which obtained by R2 is increased, but the maximum obtained for results are obtained for two hidden layers with 90% for training and 88% for testing. In figure B, you can see the comparison of deep neural network and shallow neural networks, as well as using the pre-training. It can be observed that by increasing the number of hidden layers and depths of neural network, the value of R2 increase. The interesting result is here is that by using pre-training, using a stack autoencoder, we can reach to the R2 of 97% for training and 96% for testing, which is quite higher than the SNN in the maximum cases. Trial and error approach were used in this study because there is no exact formula to obtain the optimum structure of the neural networks. We considered 7 neurons in the input layer and 1 neuron in output layer for all of the developed networks, but in the network which has the highest performance, 4 hidden layers were considered, and 24, 20 and 10, and 4 neurons are considered in each hidden layers respectively. After successful development of neural network, the model function of the network were generated using the values of weights and biases for further analysis. The results of sensitivity analysis revealed that surface modification factor with 24% has the highest importance, followed by elongation. This parameter can be considered as the parameter of surface, and this parameter can be considered as the parameter of the bulk material. These ranks are followed by surface residual stress, surface hardness, yield strength, and in the last rank, relative density and surface roughness both together. In order to apply parametric analysis, the parameters that has the highest ranks based on our obtained results of sensitivity analysis were considered to parametric analysis. Surface modification factor and elongation in terms of fatigue life. It can be observed that by increasing the surface modification factor from 0 to 1, which is related to the as-built, 0.5 is related to the shot pin, and 1 is related to the electrochemically polished sample. And also by increasing the elongation, it means that by increasing of the ductility, for example by applying heat treatment, highest fatigue life can be obtained, and it shows that these two parameters are the most important ones. This parameter analysis can be also obtained for other parameters, but in this study we just only investigate the most important parameters. And finally, the conclusions. Heat treatment considerably modified and homogenized the inhomogeneous microstructure of the as-built state of the material. Also, we obtained that surface layer gradient refinement leading to the gradient microstructure was obtained after applying shot pinning. In addition, shot pinning modified the surface morphology of the as-built state and heat-treated samples, as well as surface layer hardening by increasing the hardness in the surface and also inducing high competitive stresses compared to the both as-built and heat-treated samples. All applied post-treatments improve the fatigue behavior of the notched samples, but the highest fatigue improvement was occurred by using the hybrid post-treatments of heat treatment, shot peening, and electrochemically polishing together, respectively. Considering the sole influence of each post-treatment, shot peening has the highest effect, followed by ECP and heat treatment on fatigue life improvement. About the results of the neural network modeling, comparing to the accuracy of the obtained output of the developed network, it was obtained that pre-training in the stack autoencoder assigned DNN, deep neural network, has the highest performance. Also, sensitivity analysis showed that surface modification factor followed by elongation as a factor of ductility has the highest performance and importance on fatigue life improvement, respectively. In addition, parametric analysis revealed that surface modification factor by performing shot peening and ECP, and also by applying heat treatment to increase ductility, the fatigue behavior of material can be increased as well. As a final conclusion, it can be observed that based on the obtained result, AI-based methods such as deep learning with pre-training methods such as stacked using encoder can be used as a powerful tool for analyzing the fatigue behavior of the as-built and post-treated additive manufactured materials. Thank you so much for your attention. I will answer your questions in the scheduled time of the conference. See you.